Okay, welcome back. Operations on radicals, lesson 3, dividing radicals, part 1. So this section is actually divided into two parts because there's a fair amount to cover and two sort of different processes. So just as a quick point though, because I know we ended last video talking about multiplying by the conjugate of binomial radicals. So I want to show you real quick. If we skip to lesson 4, you don't need to flip your page, you can just watch. I'm just going to show you. So if we skip to lesson 4, the reason we need to know how to multiply by a conjugate is because when we have a denominator of a fraction that is a binomial with a radical, the process, because we can't have a radical in the denominator, the process of getting rid of that, it's called rationalizing the denominator. It's actually its formal name, rationalizing the denominator. And we do that by multiplying by the conjugate. You can see it here. And we'll talk more about that when we get there. But that's the reason why we need to know what a conjugate is. And we're going to use it, well, yeah, I guess in the next day or so. So if we go back to lesson 3, the division we're going to look at today is dividing by a monomial. And we still may have to do that process called rationalizing, but it's a bit of a different process when it's a monomial. Okay, so we have looked at this rule before. Square root of a over b is also equal to the square root of a over the square root of b, where of course a has to be greater than or equal to 0, so it can't be negative. B has to be greater than 0. It can't be 0 because as soon as you divide by 0, it's undefined. So just some other things or rules that we have to state in order to do the questions. And A and B belong to the set of all real numbers. So we can't have irrational numbers. Okay? Sorry, not irrational. We can't have non-real numbers. So all the numbers we kind of know already. We can use this rule to divide fractions in the form of, so if we have fractions with coefficients, we use the same rule. Okay, we can use the same rule. So all of these three rules can all be used kind of interchangeably. The only difference down here is that we have coefficients now in front of those radical signs or the symbols. And that just means that we have to reduce the m and the n, just like a normal fraction, okay? Because fractions are always reduced. To divide radicals, the index of the radical must be the same in each radical. You divide the numerical coefficients by the numerical coefficients, so the numbers by numbers outside. We can divide the radicands by the radicands if they're on the inside, and then of course always simplifying into mixed radical form. Now, depending on the question, it's going to depend on the process, and you can use them, like I'd said, you can use these three interchangeably. So however you need to manipulate your radical to get your simplified form, you're allowed to do. So example number 1. And yesterday I did start by saying, hey, you know what, if we can simplify a radical, sometimes it's the easiest way to go. But if we look at this and we're asked to simplify, square root of 30 doesn't simplify. Square root of 30 is the square root of 5 times 2 times 3. There's no pairs. It's not going to simplify. So we're stuck with 30. Right? Same with 6. 6 is just 2 times 3, so we're stuck with 6. But this can also be written using the above rule. This can also be written square root, all big square root, 30 over 6. And 30 over 6 reduces. 30 over 6 reduces to 5. So this is square root 5. One use of the rule. Another use of the rule, well, the same rule actually, same usage. 8 cube root 21 over 2 cube root 3 can also be written as 8 cube root, 8 cube root, but I want the 2 by itself, there we go. Big cube root symbol, 21 over 3. And again, 21 is just 3 times 7. That's not going to help us. And 3 is just a prime number. That's not going to help us either. But you can see we can simplify the fraction. The 8 over 2 simplifies to 4. And 21 divided by 3 is equal to 7. So 4 cube root 7. Question C. 15 square root 48 over 10 square root 6. Now I can see that 6 goes into 48. So I'm going to write this as a big radical. So it's going to be 15 over 10, big radical, 48 over 6. Well, 15 over 10 reduces. If they both divide by 5, that's going to be 3 over 2. And 48 by 6 is equal to, 48 by 6 is 8. Okay. But remember, it does say simplify where possible. And you should know by now that the square root of 8 simplifies. You should know, hopefully you should know, that the square root of 8 simplifies to 2 square root 2. That's a bad pen to use. What am I doing? 2 square root 2. So I could rewrite this as 3 over 2 times 2 square root 2. And then, of course, when I multiply the fractions out, because this is technically over 1, these 2's will cancel, and I'm just left with 3 square root 2. Okay? And then question D. Question D, 4 square root AB over 12 square root A is also equal to 4 over 12 square root AB over A. And these A's will cancel. Cancel, just left with B. The 4 and 12 both divide by 4. This would be 1. This is going to reduce it to 3. So this simplifies to 1 over 3 square root B. And you can write 1 over 3 square root B. You can write 1 square root B over 3. You could write 1 over 3 square root B. Whatever you need to do to make it look proper, I guess. And just know, depending on the fonts that get used, it'll depend on what the final answer will be written like. That was example 1. Example 2, and it says, in some cases, converting radicals into its simplest mixed radical form before dividing will make calculations easier. Okay, so that's a bit of a hint. Question 2, or example 2, question A, 4 square root 54 divided by 3 square root 8. So if we try to simplify these before, then somewhere we would do some scrap work and try and simplify the square root of 54. Well, 54 is 2 times 27, which is 3 times 3 times 3. It's square root, so there's our pair of 3's that's coming out. I'm left with 2 times 3 on the inside, so that's 6. So this is going to be 4 times 3 square root 6 divided by 3 times square root of 8, and we know that square root of 8 is 2 root 2, so it's going to be 3 times 2 square root 2, which is equal to 12 square root 6 over 6 square root 2. Not finished yet because we have that radical in the denominator, so I'm going to go 12 over 6. I'm going to make one big radical, 6 over 2. Well, 6 divided by 2 is 3, and 12 divided by 6 is 2. So this simplifies to 2 root 3. Question B, 8 square root 126 divided by square root of 112. 112. 16 times 7, okay? 8 square root 126. So 126 breaks down into, so somewhere, scrap work, you're going to go 126, 2 and 63, 3 and 21, 3 and 7. So square root of 126 is going to be, there's our pair, 3, and left over 2, 7, 14, 3 square root 14. 8 times 3 square root 14. And 112, that's 2 and 56, which is 2 and 28, just 2 and 14, which is 2 and 7. 2 2's, 2 2's, so this is going to be 4 root 7, all over 4 square root 7. I can go 8 times 3 is equal to 24, square root 14 over 4 root 7. And then, of course, I can simplify. 24 by 4 is 6. Square root of 14 over 7 is equal to the square root of 2. Whoops, wrong 2. So this is 6 square root 2. That's a nasty square root. Square root 2. You can do this with cube roots too. The only difference is now you're looking for groups of 3. And the more you start to work with these numbers, the better, or not the better, the faster they'll start to come to you. Okay, so 162, somewhere in my scrap work, I'm going like this. 162 breaks down into 2 times 81, which is 9 times 9. So I could actually stop there. This is going to be 9 square root 2. Okay. If you need to see it further though, just in case, here we go. This is going to be 3 times 27. This is going to be 3 times 9 and 3 times 3. There's a group of 2. There's a group of 2. Those two are going to come out. 3 times 3. Left with a lonely 2, 2, or 9 square root 2. So this is going to be 10 times 9 square root 2 all over. I do the same process for 128, which is 2 and 64, which I know is 8. So 2 times 32, oh, we got a lot of 2s. 2 times 16, 2 times 8, 2 times 4, 2 times 2. There's a group of 2, there's a group of 2, there's a group of 2. So that's 3 2s. So this is 2 times 2 times 2. Lonely 2 left over. So 8 square root 2. 20 times 8 square root 2. Okay. Now, just like variables, when I have 2x over 3x, these x's will cancel. The same goes for the root sign. If they're exactly the same, then they're going to cancel. But I'll show you the intermediate step and how they do cancel. 10 times 9 is 90, square root 2. 20 times 8 is 160, square root 2, which is equal to 90 over 160. Square root 2 over 2. Well, square root of 2 over 2 is 1. So this is equal to, well, I'm going to take off a 10 here. So divide by 10, 9 over 16. Square root 1, but the square root of 1 is just 1. So this is just 9 over 16. Fraction actually just disappeared. Except that, and I wish I knew how to edit video, except that this is cube root. Cube root. So I need to be looking for groups of 3, not groups of 2. So really, all of this is going to be wrong. And we'll have to go back to our pairings too. So if we're looking at 162, 162 breaks down into 2 times 3 times 3 times 3 times 3. That part's correct. This part is not. But I'm looking for groups of 3. There's my group of 3. That will give me a 3 on the outside, and I'm left over with 6. Cube root 6. This is 10 times 3 times cube root 6. And then 128, again, looking for groups of 3. And there's one group of 3, and there's another group of 3. So that's going to give me 2 times 2 with a cube root 2 left over, which is 4 cube root 2. That's better. 3 times 10 is 30. Cube root 6 over 4 times 20 is 80. Cube root 2. Zeros will cancel. And I can write this as 3 over 8. Cube root 6 over 2. And 6 over 2 reduces to 3. 3 over 8. Cube root 3. That's much better. Much, much better. Now we go on to example number 3. Of course, what do you think we need to do here first? We need to simplify each of the individual terms so that we could do this both ways. We need to do this both ways. Maybe we will do it both ways in a second. So let's simplify all of these first. Square root 24, square root 48, square root 108, square roots, not cube roots. So somewhere in my scrap work, I'm doing 24. 24 breaks down to 2 times 12, which is 2 times 6, which is 2 times 3, square root. So this is 2 root 6. 2 square root 6. 24, 48. 48. If you know your perfect squares, you should know that this is 16 times 3. So this is square root of 16, or you could go 2 times 8, 2 times 4, 2 times 2. Looking for square roots, 2 and a 2, left over 3. 4 square root 3. And then 108, 108 I can fit over here. 108 is 2 times 54, 2 times 27, 3 times 9, 3 times 3, pair, 6 left over 3, square root 3. 2 root 6, 4 root 3, 6 root 3. I'm not going to remember that. So 24 is equal to 2 square root 6 plus 48 was 4 square root 3 and 108 was 108 6 square root 3. 6 square root 3 all over square root 6. Now, here you can see we run into a bit of a problem. The problem is that these here and here are not going to reduce, are they? Neither are these. So that's a problem. So that means that we can't necessarily do this question this way at this point. We're going to learn a process in which we can, but we're kind of stuck. So we don't want to do that. Stuck there. So now we have to go back to, and actually that's what the question does tell us to do, divide each term by the numerator. So now I split this into square root of 24 over 6 plus the square root of 48 over 6 minus, not plus, minus the square root of 108 over 6. That's so bad. So bad, so messy. Well, 24 by 6 is 4, so that's the square root of 4. Plus the square root of 48 over 6 is the square root of 8. 48 by 6 is 8. And 108 by 6, 108 by 6. 108 by 6, 6 goes in 10 once, and it goes into 48, 18, square root of 18. But we still have to simplify. Square root of 4 is 2, plus square root of 8 is 2 root 2, which we know, and 18 minus 3 square root 2. The 2 has nothing to combine with, it stands alone. 2 root 2 take away root 2 is negative square root 2. And that would be simplified. Go over the page. Over the page now we start talking about what we call rationalizing the denominator. So this rationalizing the denominator is just like saying, remember we were saying that, oh, and there's an example right there. Remember I was saying that you can't have fractional answers that can be reduced as final answers. You have to simplify them and reduce them. Well, it's a similar rule with radicals. You cannot have a radical in the denominator of a fraction. So there's a process. The process is called rationalizing the denominator, making the denominator a rational number. So basically saying eliminate the square root. Okay? When it's a monomial, such as these examples today, binomial, we multiply by the conjugate. I told you that already. But when it's a monomial, you simply just multiply by something that's not going to change the question. So we're going to multiply by a fraction that doesn't change the question, which means we multiply the top and the bottom, or the numerator and the denominator, by the same thing. And that thing is whatever that radical symbol is. Multiply by square root 13 over square root 13, which is essentially like multiplying by 1, because that reduces to 1. So we're not really doing anything to the question. We're just manipulating and changing it around. When we multiply that, 1 times square root 13 on the top, on the numerator, is square root 13. On the denominator, square root 13 times square root 13 is the square root of 169. Well, the square root of 169 is 13, right? So the square root of anything squared, 13 squared, is just going to be that thing itself. Now we have a fraction. no radical in the denominator, so we have rationalized that denominator. And that's the process that if we were doing this question back the way I originally started it, now that's the next step I would have to do, is rationalize the denominator because I have that square root 6 in the bottom. Continuing on with our examples, square root 5 over square root 2. I can't make one big radical like this and go 5 over 2 because 5 over 2, 5 over 2 doesn't simplify, it doesn't reduce. So now I'm stuck. So I rationalize the denominator. Multiply by, what's the denominator? Square root 2 over square root 2. Well, 5 times square root 2 is square root 10. Square root 2 times square root 2 is square root 4. Square root 4 is 2. Done. Radical sign or radical symbol is gone, disappears. Question C. Again, you just multiply by that radical. Multiply by square root 6 over square root 6. We don't have to concern ourselves with the coefficient. This is a -1 coefficient. We don't need to concern ourselves with that. And many students tend to try and do that all the time. It just makes your numbers bigger. So you don't have to do that. You can if you want. You'll still get exactly the same answer, but you don't have to worry about it. This leads us to square root 12. Whoops, square root 12 on the top over negative square root 36. Well, square root 12 simplifies to 2 root 3. 2 times 2 is 4 times 3 is 12. So you have to simplify. Square root of 36 is 6. So this is -6. And then, of course, the 2 and the 6 reduce. Square root 3 over -3. And D. Square root 20 over 3. I'm going to rationalize the denominator. I'm going to multiply by square root 3 over square root 3. This is going to turn into square root 60 over square root 9. Well, square root 60. 60, 2 times 30, 2 times 15, 3 times 5. So it's 2 square root 15. 2 square root 15 all over 3. And in this case, you're done. There's no reducing. Nothing else needs to be done. Example 5, letter A. The process doesn't change if the numerator changes, so the same thing is going to apply down here. I'm just going to multiply. I'm going to rationalize the denominator, multiply by square root 7 over square root 7. The top becomes, the numerator becomes 7 square root 7 over 3 square root 49, but the square root of 49 is 7, so this is 7 root 7 over 3 times 7 square root, oh no, square root disappears, it's supposed to disappear. Well, 3 times 7 is 21, or you can see that these are going to cancel, these 7s are going to cancel right here. They're outside the radical, they can cancel. That's going to give me square root 7 all over 3. And then there's just different ways to manipulate the question to make it look a little bit different. Okay. So we can see that in question B here, that 18 doesn't reduce by 5. And this is technically, if we have fractions inside a radical, they're technically not as simplified as they can be, although they look more complicated after. So I have to do this first step. I'm going to go square root 18 over the square root of 5. I know the square root of 18 is equal to 3 square root 2 all over square root 5. I can't have that radical in the denominator, so I'm going to multiply by square root 5 over square root 5. This will be 3 square root 10 all over square root 25. Square root of 25 is 5. 3 square root 10 all over 5. Question C. Question C brings us to the question in which maybe we should reduce or simplify our radicals before we do any of our work. So if we simplify square root 12 which is 2 times 3 times 2. 2 times 2 times 3, that's 2 root 3. So this is going to become, well, root 12 is 2 root 3. So this is going to be 3 times 2 square root 3. Square root is 72. 72. 2 and 36. 2 and 18. 2 and 9. 3 and 3. There's a pair. There's a pair. That's 6 square root 2. 6 square root 2. So this becomes 6 square root 3 all over 6 square root 2. The 6's will cancel. Square root 3 over square root 2. And I need to rationalize. Times by square root 2 over square root 2. Just square root 6 all over square root 4. Square root of 4 is, oops, not 4 there, that's a 6. Square root of 4 is 2. Done. And I think I'm going to save example 6 as an in class because it's a good way to show both processes, dividing by the numerator or rationalizing the denominator. Okay, so I'm going to save this for in class. Okay, remember, you're checking Stellantis to make sure that you know which questions are suggested work for you to do, and we will see you next time.